Hello. So today we're going to begin discussing MOSFET transistors and how they work. Uh, and this is going to be in the form of several videos, but we're going to start by discussing MOSCAPs, which are metal oxide semiconductors, which are one subcomponent of a MOSFET that we'll see. So first we're going to discuss how MOSCAPs work, and then we'll use that to build onto what a MOSFET is. So as I mentioned, metal oxide semiconductor. So what that means is these devices are built using a metal that's connected to some kind of insulator, which is then connected to a semiconductor, which can be either doped N-type or P-type. For now, we're going to be looking at P-types and how they work, but we'll also look at N-type to see how they're different. Although you can kind of think about already what the differences might be. And then insulator in the middle, and then at the end is a metal or some kind of conductor. And now, the first thing we want to do is we're going to label some quantities for the band diagram of a MOSCAP to kind of understand the key properties we need to know for a MOSFET, or sorry, a MOSCAP. And one thing I'll also mention is, as we'll see, the MOSCAP behaves like a capacitor, and we'll see that as we go. But first, let's draw the band diagram for a MOSCAP when there's no applied voltage, that is, when it's at equilibrium. So we have our metal, and we have our semiconductor. Like this. And here we have the Fermi level of the metal. And here is the Fermi level of the semiconductor. And then we can label like the valence band, the conduction band, the intrinsic energy level, and then because this is a p-type, it'll have more holes than electrons, so we'll draw it like that. And now we're going to label some of the key components. And then one more energy level is the vacuum energy, which we'll label up here, E vacuum. Right. So now the key metrics we need to know. Before we go into some of the other key properties, we should also discuss what electron affinity and what work function are. So the work function is described as the energy difference between the vacuum and the intrinsic energy, E sub I. Right? The work function is important, or sorry, not E sub I, and the Fermi level, E sub F. The work function basically describes how much energy it takes to remove an electron, which is existing at the Fermi level, right? And this, I should mention, is dependent on doping concentration, which makes sense because the Fermi level is dependent on doping concentration. And then our electron affinity, which is labeled with this symbol, is described as E vacuum. minus E conduction band. This is called, again, the electron affinity, and this is not dependent on doping. It's intrinsic to the material. And so we can label now the work functions and the electron affinities. So here is labeled the work function for the metal. Here we can label the work function for the semiconductor. This is the electron affinity for the semiconductor. And then finally, this value here is the energy, is a key value. It's the energy difference. We label it as QBP, and it's the energy difference between E sub I and E sub F. Great. Now, these are the key properties of a semiconductor, of a MOSCAP. These are key quantities we need to know. And one thing I should also mention is add V sub G. You might have noticed this, but add V sub G equals 0, Q phi sub M equals Q phi sub S. Or in other words, the Fermi level for a metal is equal to the Fermi level for a semiconductor. And here, this is, if you've studied semiconductors before, you know that this is a known quantity. This equals Boltzmann constants times temperature times the natural log of, in this case, P over N sub I. And we can describe phi sub S, or the work function of the semiconductor, as equaling the electron affinity, which doesn't change depending on doping, plus the band gap divided by 2, plus this quantity here, the energy difference between E sub I and E sub F S. Great. So now that we understand what V sub G is, what the key properties of a MOSCAP, we're going to see what happens when we apply various voltages to it. So suppose we apply a voltage, V sub G is less than 0. What happens is, so we have our metal, we have our insulator, we have our p-type, what happens is the metal accumulates negative charges because the voltage is less than 0, which causes the p-type to accumulate holes at the end to match the charge deficit. This is called accumulation because you're accumulating holes. And as one could expect, this charge accumulation leads to a increase in the electrostatic potential of the p-type, at least at the edge where there's this accumulation of charge, which you can show using Poisson's equation, right? Where there's charge, there's going to be positive charge, there's going to be an increase in the potential positively. And then this will lead to band bending upward, as I will show in just 1 second. So what the band diagram for this looks like now is we have our insulator and E sub Fm remains the same, but now the band bends towards the edge, like this. And this is due to the increase in the electrostatic potential. Our E sub Fs still remains right next to E sub Fm, but our intrinsic energy level bends with the conduction band and the valence band. And now we have this accumulation of holes at the edge. And if you put a strong enough applied voltage, these holes will also accumulate also on the, You have an accumulation of holes on the end, and if you apply strong enough voltage, they'll even appear on the valence side where it's supposed to be just bulk electrons, mainly. Similarly, if you were to apply a negative voltage, V sub G, or a positive voltage, V sub G is greater than 0, then you would have an accumulation of positive charges on the metal, which would cause there to be negative charges at the p-type. And what this looks like as a band diagram is, instead of bending upward, it would bend downward, like this. And we still have E sub Fs equals E sub Fm. And our intrinsic energy appears like this. And you can see how the intrinsic energy is now crossing the Fermi level. So in practice, when we have a MOSCAP that uses a p-type semiconductor, we really only ever apply a positive voltage to it, and that's because if you apply negative voltage, you're just accumulating holes. Oh, and I should mention, this is called depletion, right? Because the other one's called accumulation. But you're just accumulating holes if you do a negative voltage, and this is kind of pointless because a p-type already has an excess of holes, so you don't really notice much band bending, in the same way that if you were to apply positive voltage, you get an accumulation of electrons, which will cause more significant band bending, and also importantly allows for this crossing between E sub I and E sub Fs, which is very important for properties that we'll look at in just a minute. And so we're going to focus our attention with the p-type semiconductor on when the applied voltage is greater than 0, and then when we look at the n-type semiconductor and its behavior, we're going to look at we will apply a negative voltage to it. So now let's look in greater depth at what happens when V sub G is greater than 0. Right? So if we were to apply just a small V sub G to the MOSCAP, then, as I've drawn before, we get a slight accumulation of negative charges, only slight. And so the band only bends slightly, with only a small accumulation of electrons at the edge. So if I draw this, draw a small band with a small accumulation of holes at the end, of negative charges at the end, and that too mainly in the valence band where there's already an excess of electrons. And I can draw E sub I. And you can see there's not even a crossing between, there may not even be a crossing yet between E sub I and E sub Fs. I'll draw the metal like this. Perfect. Now suppose we were to apply a slightly greater voltage, and there's a specific threshold. We'll go into this more, but we'll add a threshold V sub t. When we get to this point, then there's even further accumulation of positive charges, which causes further depletion here, further depletion, and which causes further band bending to the point where E sub Fs is significantly intersected with E sub I. And there's significant accumulation of holes both in the top and the bottom layer. And then finally, if we have, and we call this inversion, I should say, when the depletion gets so large that we reach this threshold voltage, it's called inversion. And then once we get to applied voltage being greater than threshold voltage, the effects that we've already looked at just keep increasing with more charge depletion, more electrons, and then more band bending. And this V sub t, we won't say exactly what the threshold voltage of it is yet. We'll calculate that. But I will say that this V sub t occurs at the point where E sub I of bulk, of the surface minus E sub I at the bulk is twice that of E sub I in the bulk, or sorry, I should say, to keep signs same, E sub F minus E sub I at bulk. And that switch was just to maintain signs. But yes, so at this point, and I'm not going to explain what's so special about this specific equality. We'll see later on, especially when we look at MOSFETs specifically, why this quantity is useful. But for now, just understand that there's this threshold at this specific identity that allows us to reach this inversion point. And now, one more thing we will do is, now that we understand the band diagrams, let's now look at what these charges look like on a graph. So this insulator, we'll say has a width T sub OX. OX stands for oxide, since usually oxides are the insulator being used. That's why it's called a MOSCAP. The O for oxide, which is the insulator. So the charge, the charge, since this is a positive charge, we can show that it looks something like this, and then, which means that there'll be a negative charge that looks something like this on the other side. Similarly, here the diagram would look something like this, where there's a bigger charge, which causes width to increase. This is because the electrons that can accumulate at the surface at x equals 0 can be a maximum of n sub a, right? Which is whatever the doping is. And so because of that, the height peaks out at n sub a times q, which means that we have this depletion width that forms. And that depletion width would just widen as we increase above the threshold voltage. And I should say that, one second. Actually, to draw this more accurately, I would want to make this smaller and this bigger, because another key property about the threshold voltage is the threshold voltage occurs when the electrons at the surface equals that doping concentration, which is another key threshold to understand about it. Further, from these, we can use Poisson's equation to use these charges to then understand what the electric field looks like. So in this case, it would likely look something like this. And then when we have more charge accumulation, it would look more like this. And then you can continue that with the other diagrams. And so this is the electric field, this is the charge, this is the electric field, and then you can also draw the voltages, which would be, in this case, parabolic. So likely something like this. Wait 1 second. Something like this, followed by a linear part, followed by a downward slope. And you could do the exact same thing on the opposite side. Here, wait. Let me draw this a little more accurately, since these would be the exact same. Likewise here, and that would be the voltage. And we can also calculate what these different values are. So rho, we know that like the charge density has to equal Q times P minus N plus N sub D minus N sub A. In this case, we know that at least at the threshold voltage, it would equal minus N sub A times Q, since due to that accumulation of holes. And so from this, we can then use Poisson's equation, which says that d sub E over d sub x equals rho over epsilon s epsilon naught, which means that E is equal to minus N sub A Q, which is just us substituting rho, divided by epsilon s epsilon naught times W minus X, where W is this width, or in this case this width, I guess, because this is what we're looking at for inversion. This is called the depletion width. You can do the integral out to see how this is solved, but yeah. And if you take the integral of this once again, you get the voltage, which looks like this. And I guess when you take the derivative, this becomes positive instead of negative. And so you can see how we have derived some functions for rho, E, and voltage. Next. Now we can also calculate some other quantities, some other key quantities. Namely, we can calculate what the depletion width is. So using this voltage formula that we derived, we know, okay, so before we do this actually, let's define some quantities. So I guess we've already defined this, but we can say that when we're looking at these various band diagrams, we've been able to describe the potential phi of x, which is the difference between the bulk and, wait 1 second, we've been talking about E sub c and E sub v, right? And with a E sub I and our E sub f. So a key quantity that we need to label is if this is the intrinsic energy in the bulk, then this is what we call phi of x, or I guess q phi of x. So then, for example, this would be q phi sub s because it's the surface potential multiplied by q, and then we would describe this as q phi sub f because it's the intrinsic energy minus the Fermi level, which is also another key quantity. And this is important because, as we defined previously, the inversion occurs when phi sub s is equal to 2 times phi sub f. So it's important to label these because we need to be able to define phi sub s. Well, we need to define phi sub x, phi of x first, as 1 over q E sub I bulk minus E sub I of x. Now, that means that our phi sub s can be defined as this expression, but at 0 instead of x. And similarly, phi sub f can be defined as E sub I bulk minus E sub f. Which we can further rewrite using some expressions that we already know as kT over Q natural log of P over N sub I which is for p-type. For p-type, and then for n-type, we'll see this later, but because the Fermi level is higher, this is actually going to be a negative value of the natural log of p over n sub I. Now, After defining these quantities, now we can move to the part where we define the width, where we calculate the width and the threshold voltage. So the width, W, is calculated by using our voltage equation that we got here. So in this case, we can say that phi sub s, which is the voltage at which is equal to the voltage at 0, is then equal to, well, plugging in x equals 0 is equal to n sub a q over 2 epsilon dielectric constant times epsilon naught, permittivity of free space, times W squared. And so then you can rearrange this to then get depletion width. And this is how you standardly calculate for depletion width. And similarly, V threshold is equal to phi sub s plus change in phi. And this change in phi is basically the voltage drop that occurs in between the insulator. So you can see how there's this constant electric field, and that constant electric field creates this voltage drop that you see here, which you need to calculate. And you can derive an expression for that pretty easily. It's just the thickness of the oxide times sorry about that. So I pulled up the expression here. It's a little weird, but basically this describes what we just previously calculated as the charge accumulation at the surface, and then since the potential is equal to the width times the electric field, we can replace the width with the thickness of the oxide and the electric field with Q over epsilon, which is epsilon s, some dielectric constant, times epsilon naught, and we get this expression where this is Q with sub s that we previously calculated. And so this is how you get the threshold voltage. And you'll notice that this expression right here can be rewritten, or not this expression, sorry, this expression here can be rewritten as 1 over C aux, 1 over a capacitance, which is really interesting because, again, this is a capacitor. And that's how a MOSCAP works overall for a P-type semiconductor. In the next video, we're going to quickly go through how this would work now for an N-type semiconductor, looking at the band diagrams and the different graphs and then different expressions for the key properties of an N-type MOSCAP. Thank you for watching the video. If you enjoyed, please like and subscribe, and feel free to ask any comments in the question. I'm happy to answer. Thank you. Bye.